Welcome to AI Peer Review, the show that extracts the most important nuggets of knowledge from cutting-edge research and brings them directly to you. Today, we're diving into a challenge that's been, well, a fundamental dilemma in generative AI for a long time. This relentless trade-off between speed and quality. You know the drill, right? On one side, you get these incredible high-fidelity images, breathtaking stuff, but it often comes with a hefty computational cost. Super slow inference times. Think about waiting ages for that one perfect high-res picture. Then on the other side, you've got rapid, few-step generation, lightning fast. But historically, that speed comes with a pretty hard ceiling on quality. It's like choosing between a masterpiece that takes forever or a quick sketch that's, well, just okay. But what if you didn't actually have to choose? What if a single model could somehow give you both, the speed and the detail? Today, we're exploring some really groundbreaking research trying to resolve this exact conflict. We're unpacking an interesting paper called Transition Models, Rethinking the Generative Learning Objective, introducing an approach called TIM. Our mission is to understand how this new paradigm promises both exceptional fidelity and efficiency, even from a model that's, surprisingly, not enormous. Get ready for some surprising results and hopefully a few aha moments that might just reshape how you think about generative AI. Okay, let's set the stage properly. To really get why TIM is a big deal, we need to appreciate this long-standing tension. So on one side, you have the current quality champions, iterative diffusion models. Most of you listening are probably familiar with these. They work like meticulous artists, right? Slowly adding detail, layer by layer, refining an image from pure noise over many, many steps. And the results, stunning, truly state-of-the-art. But that iterative denoising needs a large number of function evaluations, NFEs. And more NFEs, as you know, means more weighting, increased latency, higher compute costs, like needing hundreds of tiny brushstrokes.
Exactly. These models, they typically lean on numerically integrating complex differential equations. Think stochastic differential equations, SDEs, or maybe probability flow ODEs. Now, they're incredibly effective at capturing those fine details, but the math itself forces them to take many, many small steps. If you try to take too big a leap, you introduce significant errors, discretization errors, and the whole process kind of breaks down. It really is like trying to draw that perfect circle with hundreds of tiny, almost invisible lines. Each one is precise, but adding them all up takes time.
Okay, so that's the meticulous artist, the diffusion model, slow but amazing quality. What about the other end, the quick sketch guys? You mentioned consistency models or flow map. Where do they run into trouble?
Well, their whole goal is speed, right? They try to learn a direct map from noise straight to the final image, or maybe just over a few large steps, shortcut the process. The fundamental problem, though, the trade-off, is that by essentially averaging over the entire path, they kind of throw away the fine-grained local dynamics. All that subtle information needed for really high-fidelity refinement, it gets lost. And this leads directly to what we call performance saturation. You add more sampling steps, hoping for improvement, but you get diminishing returns. Sometimes it even gets worse. Their quality just hits a plateau very quickly. And that peak quality, it's usually well below what the slower multi-step diffusion models can achieve. They sacrifice detail for that shortcut.
Ah, okay. So it's not just the model architecture itself, it's deeper. It's about how they're trained, the learning objective.
Precisely. It's a foundational choice you make right at the start. Objectives designed for instantaneous dynamics, like in those PFODEs or SDEs, they scale beautifully if you give them lots of steps. They understand the local changes perfectly, but they really struggle in few-step scenarios because they just weren't built for those big jumps. On the flip side, you have finite horizon training, the kind used in things like consistency models. They learn a direct map over a fixed interval, great for few-step, but they don't benefit from more steps. There's no mechanism baked in for that gradual monotonic improvement. Add more steps, quality stays flat, or even drops. So it's been this persistent fundamental compromise. Train for speed or train for quality. Getting both in one framework that scales smoothly, that's been the challenge. Until maybe now.
Which brings us neatly to transition models, or TIM. This paper proposes a way out of this dilemma, so what's the core idea? How do they break that compromise?
The big idea with TIM is that it introduces an exact, continuous time dynamics equation. And this equation analytically defines how the state transitions across any finite time interval. Let's call it a shay. This is a really profound shift. It means the model isn't just learning tiny steps or one big jump. It's learning to navigate the entire generative path seamlessly. It can handle single, large leaps or incredibly fine-grained multi-step refinement. It becomes this versatile denoising operator where you just tell it the interval size you want.
Okay, that's different. So instead of approximating an ODE step by step or just predicting the final endpoint, Tim is learning something more fundamental, like the underlying rules of the journey itself.
Exactly. You've hit it. It's learning what the paper calls the solution manifold of the whole generative process. Now, solution manifold sounds complex, but think of it like this. Instead of learning just one specific hiking trail from the base noise to the summit image, Tim learns the entire mountain landscape. It knows every possible path, every slope, every shortcut, every scenic route.
Okay.
So it doesn't matter if you ask it to take one giant leap towards the summit or 1,000 tiny steps along a ridge. It understands the terrain globally. By internalizing this whole structure, Tim naturally gains the ability to do inference over absolutely any step size. It unifies that local step-by-step view with the big picture, finite horizon view in a single model. That's the power.
Wow, okay. Learning the whole landscape, let's unpack that magic a bit. How does Tim actually learn this solution manifold? What's the key mathematical insight?
The absolute key is something the authors call the state transition identity. It's equation 8 in the paper if you want to look it up. Now, we don't need to drown in the full math here, but the crucial thing is that this identity acts as a powerful product derivative invariant.
Okay, invariant, meaning it stays constant?
Exactly. They found this mathematical property that holds true throughout the entire generation process, regardless of the interval eon you choose. This constancy is what gives Tim its stability, especially during multi-step refinement. And this identity imposes two critical constraints during training. First, implicit trajectory consistency. This basically forces the model to ensure that any path from a starting point T to a target R is consistent, meaning a direct jump from T to R must give the same result as going indirectly, say from T to S and then S to R.
Ah, so the path doesn't matter, the result should be the same, which isn't true for other fast models.
Precisely. Standard consistency models lack this guarantee. This property is what makes Tim robust to different sampling schedules and, crucially, enables that monotonic refinement we talked about. You can always add more steps and get a better result. That's huge. The second constraint comes from unpacking that identity, time-slope matching. Most diffusion training just tries to minimize the error, the residual's value. Tim goes further. Its objective also forces the model to minimize how quickly that error changes over time, the residual's temporal derivative.
So not just how wrong it is, but how fast the wrongness is changing.
Exactly. It's a higher-order constraint. It compelled the model to learn a smoother solution manifold, which helps preserve coherence when taking large steps and ensures stable, smooth refinement when taking small steps. It's about the smoothness of the transition, not just hitting the target.
That sounds computationally demanding, especially calculating that temporal derivative for massive models. Wasn't that a major bottleneck for similar ideas in the past? How did they overcome that?
You are absolutely right. That has been a massive roadblock. Previous attempts often relied on something called Jacobian vector products, JVP, to compute that network time derivative. But JVP is, well, first, it's slow, compute intensive. But even worse, it's fundamentally incompatible with a lot of the modern tools we rely on for training huge models. Things like flash attention, which massively speeds up the attention mechanism, or distributed training frameworks like FSDP, which let us train across hundreds or thousands of GPUs. JVP just doesn't play nice with them.
So you couldn't scale those older methods up.
Pretty much. It made training billion-parameter foundation models using those techniques basically impractical. A theoretical curiosity, perhaps,
Yeah.
but not something you could actually build and deploy at scale.
Okay, so what was Tim's solution? This sounds like a critical, practical breakthrough.
It really is.
Yeah.
They introduced what they call the differential derivation equation, or DDE. You can see this equation 10. It's a principled, but very clever and highly efficient finite difference approximation for that time derivative. And the results are striking. If you look at table 1 in the paper, DDE is not only roughly twice as fast as JVP,
Twice as fast, wow.
but the really crucial part is its structure. It's a forward pass-only calculation, and that makes it natively compatible with things like FSDP and flash attention.
Ah, so it fits right into the modern deep learning toolkit.
Exactly. This is the game changer. It takes this powerful theoretical idea, which was previously unscalable, and makes it practical for large-scale deployment. This makes Tim potentially the first model of its kind that you could realistically pre-train from scratch at the billion-parameter scale. It bridges that gap between theory and practice.
That's impressive engineering. What about training stability? You mentioned it learns over arbitrary intervals. Doesn't training with, say, really huge jumps alongside tiny steps cause issues, like unstable gradients.
That's another very valid concern. And yes, training with a wide mix of intervals, especially very large ones, can introduce significant variance in the gradients. The loss signal can get noisy. So they implemented a smart fix, a loss weighting scheme. It's detailed in equations 11 and 12. Essentially gives more weight, more importance to the shorter interval transitions during training
Why the shorter ones?
because they provide a more frequent and stable learning signal. It's like grounding the learning process in the more reliable fine-grained steps, while still allowing the model to generalize to those larger, potentially noisier jumps.
Okay, so it anchors the learning.
Precisely. It ensures robust convergence, which is absolutely critical when you're training such a flexible model over potentially millions of steps.
Okay, so we have this novel learning objective, the state transition identity, the clever DDE for practicality, and the loss waiting for stability. Did they also need to tweak the model architecture itself to really make the most of this?
Yes, they did. They started with the well-regarded DIT, or diffusion transformer, architecture as a base, but made two key modifications specifically tailored for TIM. First, decoupled time and interval embeddings. That's equation 14. The idea here is to help the model clearly distinguish between two things: the absolute time to, like, where are we overall in the process from noise to image, and the specific transition interval. It's currently focused on how big a step are we taking right now.
So it knows when and how far.
Exactly. They use two separate time encoders, one for T and one for yacht, and combine their outputs. This combined embedding gives the model much richer temporal context, crucial for handling those arbitrary intervals. The second modification is interval-aware attention, shown in equation 15. This is quite insightful. They realize that the best way to model spatial relationships in the image probably depends on the size of the jump, on ad sheet.
How so?
Well, think about it. If you're taking a huge leap early on, maybe from noise to a rough shape, you need the attention mechanism to focus globally on core structures. But if you're taking a tiny refinement step later, adding texture, you need attention to be very local, very fine-grained.
Right, standard attention doesn't really know the difference.
Exactly. It treats all steps the same. So with interval-aware attention, they actually inject information about agent's magnitude directly into the query, key, and value computations of the attention mechanism. This makes the attention itself context-aware. It can adapt its focus dynamically based on how big a step the model is currently taking. Pretty clever.
Okay, we've gone deep into the mechanics, the how. Fascinating stuff. But let's get to the payoff. What does this all mean for the images? How does Tim actually perform? This is where it gets exciting, right?
Right, the results.
Yeah.
And they are quite compelling. On the GenBell benchmark, which is designed to assess generative model quality and alignment, their TIM model, which is only 865 million parameters, relatively compact these days, actually set a new state-of-the-art.
Okay.
And here's the kicker. It outperforms several much larger industrial models. We're talking giants like ST3.5 large, which has 8 billion parameters, and FLUX.1 dev with 12 billion.
Wait, an 865M model beating 8B and 12B parameter models. That's really something. What does that tell us?
It's a huge statement, isn't it? It strongly suggests that the learning objective might be more critical than just throwing more parameters at the problem. A smarter paradigm can be more efficient.
Right. More efficient learning.
Exactly. And remember that monotonic quality improvement we discussed, the idea that more steps should always mean better quality.
Yeah, that seemed like a key advantage.
Well, Tim delivers on that promise. If you look at Table 5 in the paper, it's crystal clear. Kim shows consistent, monotonic improvement as you increase the number of function evaluations, NFEs. For instance, he gets a solid Generative score of 0.67 with just one step. One NFE?
Wow, 0.67 in one step is strong.
Very strong. And it scales smoothly up to 0.83 at 128 steps. Now, compare that to others. SD 3.5 large, for example, really struggles or even collapses at very few steps. And something like FLUX.1 Schnell, designed for speed, actually starts to degrade in quality if you give it too many steps.
So Tim avoids both pitfalls.
Exactly. It truly offers flexible, any-step generation where adding compute consistently yields better results. That's been elusive.
Okay, strong on Generative. What about other benchmarks? Fidelity. Efficiency comparisons.
Good questions. On the MJHQ30K benchmark, which focuses on high-resolution image quality, Tim achieved a new state-of-the-art FID score of 5.25. That indicates really superior fidelity. And for efficiency, on the DPG benchmark, an 8 NFE TIM model, so just 8 steps, actually outperformed established models like SDXL running at 100 NFEs.
8 steps beating 100 steps.
Yeah. It's not just about reaching high quality eventually. It's about getting there much, much faster. That really drives home the efficiency point.
And resolution. A lot of fast models struggle with native high-res generation.
Right, they often rely on separate upscaling stages. But Tim, using their native resolution strategy, performs exceptionally well directly at high resolutions,
Mm-hmm.
up to 4096 by 40 on 96 pixels.
Whoa!
And importantly, it also generalizes well across different aspect ratios, which you can see visually in Figure 1 and check the numbers in Table 6. This makes it much more versatile for real-world use cases beyond just square images.
The paper also includes ablation studies, right? Table 4, I think, where
Yeah.
they test the impact of each individual component. Those are always revealing.
Absolutely. Rigorous ablation studies are crucial. And yes, Table 4 confirms how important each piece is. Just switching from a standard diffusion objective to the TIM objective using their DDE calculation, that alone dramatically improves two-step performance. It cut the 1 NFE FID score by more than 6 times.
6 times better in one step, just from the objective change.
Massive difference. And then adding the decoupled time embeddings and the interval-aware attention on top consistently gave the best results across the board from one step all the way to many steps. It shows all these components work together synergistically.
Okay, so summing this up for our listeners, especially those working in the field, what's the big takeaway here? How does Tim change the game?
I think this work is genuinely a significant leap forward. Tim isn't just another model hitting soda on a benchmark. It feels like proof of a more powerful, more unified generative paradigm, achieving that monotonic quality improvement, scaling from one step to many, reaching ultra-high resolutions, and doing it all with a relatively compact 865M parameter model. It demonstrates that this unified approach isn't just possible, it's actually superior. We really think this paves the way for a new generation of foundation models, models that are simultaneously efficient, highly scalable, and creatively potent. It could unlock real-time applications, much faster iteration for artists and designers. It really lowers the barrier to high-quality generation.
That's incredibly exciting. It genuinely feels like a step change. But of course, no research is ever completely finished. What limitations do the authors themselves point out?
Right. Responsible research always acknowledges limitations. They mention a few key areas. First, ensuring content safety and controllability. Making sure the model generates what you want and avoids harmful content remains an ongoing challenge, as it is for most large generative models. That needs more work. Second, while the fidelity is excellent overall, they note it can still struggle with extremely fine-grained details sometimes. Think rendering perfectly legible text or getting human hands consistently direct notoriously tricky areas.
Yeah, text and hands are tough.
Exactly. And finally, they did observe some occasional visual artifacts when generating at the very highest resolutions, like 3072 by 4096. Interestingly, they suspect this might be due to limitations or biases in the underlying VAE, the autoencoder used, rather than a fundamental issue with the TIM process itself.
Ah, so fixing the VAE might fix those artifacts.
Potentially, yes. It points to avenues for future improvement, maybe pairing TIM with even better autoencoders down the line.
So there you have it. Transition models, Tim. A fascinating attempt to fundamentally rethink how generative models learn. It seems to successfully unify the speed we want from few-step models with the incredible detail we expect from multi-step refinement, all within a more efficient package. It's a really remarkable achievement that challenges those old assumptions about the unavoidable trade-offs in AI image generation. And that brings us to our final thought for you to mull over. As we get models like Tim, capable of high-quality generation at seemingly any number of steps, what new creative frontiers does that actually open up? Think about truly interactive image creation, tools that respond instantly but can also refine endlessly. Or maybe completely new forms of dynamic visual media. And perhaps more fundamentally, how might this shift in focus from modeling static points or fixed jumps to modeling the transitions themselves influence how we develop other kinds of AI? Could learning the how of change be the key to more adaptable, more intelligent systems across the board? Maybe the next big leap isn't just bigger models, but fundamentally smarter ways of learning the dynamics between states. Something to ponder.